Welcome to this next session on smart contract security. We have 4 very interesting talks in this session. The first one is an invited talk by Dan Robinson. And Dan is a general partner and the head of research at Paradigm. I'm sure all of you have heard about Uniswap, and it's a major milestone in the history of DeFi. And today we'll have Dan tell us about Uniswap v4 and future research directions for decentralized exchanges.
Hi, everyone. So I'm Dan Robinson. I work at Paradigm, which is a crypto asset investment firm. And I should disclose that we are invested in some of the projects that I mentioned today, including Uniswap. And in general, just have a lot of investments, friends, biases, people I know in the space, and sort of on a research agenda to push. So I'm not promising here that I'm going to give an unbiased talk. And also, nothing I say here is investment advice or legal advice, and I'm speaking on my own behalf and not on behalf of Paradigm. What this is an apology. So who here, show of hands, who here was at SBC last year? All right, so who here of those, who here, show of hands, saw my talk last year? All right, cool. All right, well, so this is an apology to you. So I came up here on this stage and gave a talk, and a lot of the talk was about Uniswap v3 and particularly about a phenomenon called jet liquidity. And there are some things in that talk that actually I think I've changed my views on, or I've got a little more subtle perspective on now. And so at 2 points in the talk, I'm going to apologize and talk about how my views have changed on that, on those topics. So first, I want to talk about how I think about the framework of overall DEX research. And I think, in general, DEX is very PvP, and DEX research has been PvP as well. And people tend to think of it in terms of these zero-sum games between different players. And so one of those is the game generally between swappers and liquidity providers. And I think a lot of people, when they're designing DEXs, they often think, oh, what can I do to benefit liquidity providers maybe at the expense of swappers, or benefit swappers at the expense of liquidity providers, and different DEXs take different positions on those. And then within those camps, I think people can often think, what kind of swappers are we serving here? Are we serving more professional traders and benefiting them, or we want to make it easier for amateur traders? And then there's also this parallel on the liquidity provider side, where some liquidity providers are active, and some want to be more passive, and you can design your AMM in ways that maybe favor one or another. And this is one of the dichotomies that I kind of got caught up in last year when I was talking about just-in-time liquidity. And in thinking about just-in-time liquidity, I was responding to a lot of people who said, oh, it favors active over passive liquidity providers, and that's bad, or it favors swappers over liquidity providers. And I rejected those frames, and I said, look, it's giving swappers better execution, and that's what matters. And I think I still am in favor of JIT. I still think it's important, but I'm going to talk about why I'm slightly more skeptical of JIT as a positive force in Uniswap v3. And I'll do that by explaining, look, we've got this whole picture of our swappers and our liquidity providers. But if we zoom out, this whole system, this is our DEX. These are our users. It's people who are providing liquidity or people who are trading on it. And you can shift the value around in there, but what really matters is how much value is coming into the system and where is the value leaking out. And I think we see a few places where this value already does leak out. So one way through MEV is to arbitrage. And that's this phenomenon of loss versus rebalancing, or latency arbitrage, which I'll be talking about in this talk. But that primarily is a cost paid generally by liquidity providers. Another side is slippage, which I'm using as a general phenomenon of swappers getting a worse price on Uniswap than they might otherwise. And often that leaks also in the form of MEV, of minor extractable value. Or I guess it's not really MEV, and it doesn't stand for minor extractable value anymore. It doesn't really stand for anything, which is good, because I'm not sure you would really call gas that, but that's my third one, is gas. This is ETH burned by EIP 5059, which is paid by swappers. It's given up by liquidity providers in the form of less arbitrage happening. But all of these are ways in which value is leaving the DEX system. And I think a lot of DEX research today is figuring out how do we prevent this value from leaking? And in general, our enemy here is not active liquidity providers. It's not certain kinds of traders or other traders. What it really is it's the block proposer. That's where the value is going. And so, this is why I actually, I think I apologize for how I thought about JIT was, when you think about JIT as a game between liquidity providers and swappers, I'm like, okay, it makes sense for swappers to actually be, that we benefit swappers at the expense of liquidity providers. They shouldn't be getting a worse price so the liquidity guys make more profit. But there's a third party in there, right? And that's actually the block proposer. The block proposer has the opportunity to provide the JIT, and they're making some profit from that. And that's value that's actually just not going to the swapper or the liquidity provider. And this wasn't like a shock to me that this exists, but actually when you think about it, in general, if our goal is to prevent that value from being extracted, I think we have to think about ways to reduce that and be focused more on that. So slippage, that's one of those phenomenons. We worked on a solution and released our general design for a possible solution to that, which is Uniswap X. I'm not going to be talking about that in this talk, but that's what's focused on making execution better for swappers, primarily. And then the system that we designed in order to try to help with this other problem, the problem faced by liquidity providers, is Uniswap v4. And that's what I'm going to be talking about. So the main type of loss that NEV that is on that side of that arrow, the liquidity provider side of the arrow, is what's been called latency arbitrage or loss versus rebalancing. So DEX research today is largely about reducing these kinds of MEV, and loss versus rebalancing is maybe the one that's gotten the most research. And a couple seminal papers on this by Jason Milionis et al. He presented it, the second paper on Monday. But just for a quick recap of what loss versus rebalancing is, in general, when you have an AMM, you have liquidity provided on both sides, separated by a spread. When the centralized exchange price moves into past that fee boundary and somewhere into that, this happens because blocks are discrete, so the prices can jump. So the price actually moves beyond the edge of the liquidity that's being provided net of fees. Then someone comes in and arbitrages that. So someone can come in and trade it, and their average execution price there, that's P average there, that's a better price for them than they got on the centralized exchange. That's profit made by the arbitrager, that's value leaking out of the system. So how are we going to try to prevent that? And so Uniswap v4 is our attempt to work on that. And what is the solution? We actually don't have one. We don't know a solution to lever. I'm not sure there is a solution, like an ultimate solution to lever. What we have is a lot of ideas. And the world has a lot of ideas. And I think there are better ideas that I've heard coming out of people, even the past couple of weeks, than I would have thought of myself. So we're thinking, how do we actually harness all these ideas? And I think we took some inspiration from how we thought about Uniswap v3 and how that played into the DEX research landscape at the time. So when we worked on Uniswap v3, we thought of it in some ways as a platform for the kind of innovation that was happening at the time, which, in 2019, 2020, largely AMM research was about what liquidity is shaped like. It was about if you have, with Curve, for example, which was the most successful of these other AMMs. With Curve, you had concentrated liquidity, which is good for a particular kind of asset or a particular pair of assets, stable assets. And then you had different kinds of liquidity for and curves for different kinds of assets. But you could actually use Uniswap v3 to construct any of those. So this is the graph of liquidity on the x-axis, and price on the x-axis and liquidity on the y-axis in Uniswap v3 that corresponds to all those shapes of curves that we had. So you could do any of these on Uniswap v3. But today, in the innovation that's happening, it actually really isn't about what the liquidity curve is. And in general, there's no way you can just reshape your curve in order to get rid of loss versus rebalancing. It's kind of a fundamental property of just how trades are actually happening at this microstructure level. So there's no curve that's going to eliminate loss versus rebalancing. So the solution that we had for creating a platform for this kind of innovation to happen on top of Uniswap rather than somewhere else is hooks. So hooks allow anyone to deploy new Uniswap pools that have some custom behavior. They can insert some logic into a particular callback point in the Uniswap v4 contract and execute that logic before any swap or before certain events on that pool. And today, all the hooks we're going to be talking about actually just rely really primarily on one callback, which is the before swap callback. And then I'm also going to talk about how hooks have this power to change the swap fee. So in this before swap callback, you can actually adjust the swap fee and distribute it in different ways. So hooks are pretty neat. For one thing, if you deploy a Uniswap v4 pool, your pool is cohabitating in the same contract with every other Uniswap v4 pool, which makes multi-hop swaps more efficient than they would otherwise be. You don't need to have transfers for those. Hooks have hard-coded permissions. They're actually hard-coded into the most significant bits of the address, of the hook address itself. So they're as immutable as it gets. And that determines what a hook can do. And if a hook only has the before swap permission, the one we're going to be talking about here, that actually means it's unruggable, which, you know, like, I'm just looking forward to, okay, this is definitely gonna be quoted in a lawsuit someday, you know? What I mean by this is, if you have a arbitrary logic in a before swap hook, it can't actually take the money away from the liquidity providers. It can only prevent swaps from happening, but liquidity providers will still be able to withdraw. So it'll be as if the swaps are disabled on the pool in worst case scenario, but ultimately liquidity providers will still be able to withdraw what they had at the time that there was a bug or the hook failed. So we're going to be talking about a bunch of examples, but all of them actually just use this one feature, which is the before swap hook. And in fact, they all just do something before the first swap on a pool on a block. And based on what you do in each of those, you can actually get really interesting behavior. So it's a very flexible feature. So one is oracles. So if people recall in Uniswap v2 and v3, we had to build in oracles into the core contract. Because in order to have an oracle that was somewhat manipulation resistant, you had to do something before every swap, or before the first swap in every block. And so we built in this TWAP oracle that was trying to be relatively neutral and unopinionated. But if you wanted to do something different in a pool, for example, if you wanted to reduce the manipulation resistance of the TWAP oracle by Windsorizing the prices, by removing outliers in recent prices, you could design that in Uniswap v4 and you could introduce it into a pool. If you wanted to measure something different, if you wanted to measure something like volatility or an exponentially weighted TWAP, you could add that into a pool. So I think we want to see like a lot of people trying different things with how you could do oracles. Now, I think there's a lot of challenges with oracles. One of the biggest ones is there's this free rider problem where swappers ultimately, the first swap in the block is paying for oracle updates, not whoever's using those oracles. And that seems like it may be unsustainable, but maybe an oracle hook could figure out how to actually make it worth the cost for swappers and have people using the oracle pay for it. I'm not sure. TWAP oracles in some cases are vulnerable to manipulation. If you trade to a really high price on a TWAP and trade it back, you could potentially significantly move the TWAP over some period. So again, some solutions maybe like Windsorization could particularly address that. Curious to see what people do. And finally, TWAP oracles inherently lag current prices. I'm not sure the best way, if you need a really recent price, what the best approach would be there, or whether that's just sort of fundamentally not the kind of thing you can use an on-chain TWAP oracle for, but would be curious to see if anyone has solutions to it. So another hook, type of hook I'll be talking about for this one for lever reduction is this idea of dynamic fees. And that's a fairly broad idea, but I'm going to talk about one example of it that was invented by Alex Zlobin and talked about on a Twitter thread he did. Which I really like this concept. And this is something that's cool. It could have been done in Uniswap v2 or in Uniswap v1, but it wasn't. And again, because nobody thought of it at the time. But like now, you can actually just build it into any pool you wanted to release on v4. So people could just go and try it out with low overhead. So in this idea, you have recall we have this AMM. That has some price. Now, when the centralized exchange price moves beyond this no arbitrage window, generally the pool gets arbed. And there's nothing in this thing that we can do about that. But what do we do after that? So what do we know about if the pool has been arbed, if the price of the pool has moved in a recent block? I think one thing we could kind of infer from it is that the centralized exchange price actually is maybe more likely to be closer to that boundary, right? If the pool has been arbed, that means maybe the centralized exchange price is actually at the top boundary. And in that case, this is the wrong place to put our AMM price. You're charging like twice as much fees to trade in one direction as you are in the other direction relative to the centralized exchange. So what you can do, and this is a relatively modest change, you can just shift that a little bit. You don't want to shift it too much because it could result in certain kinds of manipulation attacks. But you can shift this a little bit so that there's a bit more of a spread on the other side. Basically taking as a signal, as almost a kind of on-chain oracle, this recent price move, telling you that the centralized exchange price is higher than your pool's price. So there's some challenges to really making a robust leverage solution out of this. One just mechanical one is fees can't go below 0, and if we don't want to have like permanent losses, we don't really want to mess with the fees that much and have the prices go way off of where they are. So it gives you only a little wiggle room. Sometimes signals might require off-chain oracles, like about the price of a recent price on Binance, for example, and that requires some kind of off-chain infrastructure. And in general, a lot of these hooks ideas, so this was a relatively simple one, but a lot of them depend on this idea, can we distinguish between informed and uninformed flow? Maybe by the address it comes from, maybe by the size of the flow. But there's a game there where if you're discriminated against that, then whoever is the informed flow can come in and they can act like uninformed flow. They can basically figure out how to game that signal. And so figuring that out, I think, is a difficult active research problem. So another example is of what you can do with the hook for lever reduction is what I'm calling like ex-ante auctions. And that's just auctioning. This is proposed originally by Alex Herman as this idea MCAMM, MEV capturing AMM. But the core idea is that you auction off the right to trade on to be the first trade on a block, that ARB capturing trade, prior to that block. So you have some kind of on-chain auction. It could be an on-chain auction that runs over several blocks, so it's somewhat manipulation resistant, for the right to be the first swap in block n. So it's settled by block n minus 1, who is going to actually have the right to be the first swap. And that 5 ETH, that winning bid is paid to the liquidity providers, whether or not you actually make ARB profit on that. Now notice, this is effectively an option, what you're buying if you bid on this in this auction. You're choosing, okay, like I think this is what the price movement will be, so I'm going to pay some amount up front. That's a more complicated problem than just an atomic ARB or even a statistical arbitrage. So it might require more sophisticated parties, and it's more difficult. I'm worried that there are some games that proposers could play with this, where they can maybe in the last possible moment censor bids or censor trades and then bid in an upcoming auction at the same time. So I think figuring out those mechanics is a little bit difficult. And then also distributing rent to concentrated liquidity. Distributing that bid is non-trivial because arguably you want to pay everybody who actually gave up any option value in that. And then finally, if the winning bidder doesn't trade, maybe you don't end up with any. You won't have any trades on the block at all. So that could be a problem. Another type of design is we're calling ex-post auctions, and that's an auction that happens after the volatility has been realized, after trades have happened in the block, but after the SEX price has moved, but before the block has been committed, and so that more or less has to happen off-chain because otherwise the proposer could censor bids on it. So. I think it's potentially a lot more powerful than an ex-ante auction, but it means you need some kind of off-chain auction, which requires either trusting some third party to run this auction without censoring or peeking at bids, or having some kind of trustless system that performs that function. I think it doesn't take away the power of the proposer to still just prevent any trade from being included on the block, including preventing the ARB trade from being included. So that could allow some kind of games that the proposer or block builders could play. It introduces a little additional latency into block production. You have to run this auction basically after the SEX price has moved, but then you have to have some kind of bid process, and then they have to distribute that the winning bid. Whoever's running the auction has to distribute the winning bid to block builders. Ultimately, if there's some kind of consensus protocol in there, potentially that adds some additional latency. So all of that introduces a little difference between the SEX price and when it actually gets settled on chain. And finally, there's mixed evidence right now on how competitive on-chain auctions are, especially for mid-tail or longer-tail assets, but even for some of the top assets. And so I think there's a question of how competitive this would be. But again, I think a lot of smart people working on solving problems like this. Final example hook that I'm going to talk about is one that implements TWAM. And so the way TWAM works is this is an idea that's proposed by my colleague Dave White a couple of years ago in a paper that we published. And the idea is you can allows people to set these TWAP, these long-term orders, these TWAP orders, buys or sells, that will get executed on chain over time. And the guarantee provided by the pool is that these trades have to be will be the first in every block. You'll break this trade up into small pieces, and you will trade it, execute it as the first trade in every block. And in fact, it's computed such that it's as if actually time was continuous, and you split these trades up into infinitesimal amounts and just alternated between infinitesimal buys and sells in between blocks. So it's a cool idea. It allows these interesting features, like a user experience that you might want of executing a TWAP. It also allows avoiding certain kinds of MEV, like it's much harder to sandwich a TWAP order. And I think it's interesting from a loss versus rebalancing perspective potentially, because this is known to be uninformed flow, because it's TWAP flow in general. And so I think that it's interesting to think about, could we provide much more of a discount for TWAP orders and fees potentially, because we know that it's not actually informed flow in some sense. It's not informed in the sense that it can be argued against a centralized exchange. But yeah, so I think there's some challenges with TWAM as well. And again, I think the biggest one is just gas that has to be paid when you swap on TWAM. And so again, I think like it's ultimately the gas cost of the TWAP orders is paid by the first swapper in the block. And so it's another kind of potentially a free rider problem. And so figuring that out and implementing this efficiently is a problem. And I know some people are working on it as well on V4, but we're very curious to see what people do. We do have an example implementation actually of TWAM, a prototype implementation of it in the V4 repo. So I only really talked about one hook and the ability to modify fees. There are other nice features of Uniswap v4. It has these other callbacks. There's just some examples. There's an after swap function. That's often useful if you want to distribute fees after the fact to whoever you traded against, for example. There are before modified position and after modified position hooks that apply to liquidity providers. And those, unlike the before swap hook, those are not unruggable hooks. Those are hooks where potentially, if you haven't audited the code that's being used in the hook, maybe this could cause your liquidity to be locked. But that's it's another set of things that you could potentially do with hooks and kinds of pools that you could build. There's some other cool things about v4. It implements native ETH for the first time since Uniswap v1. It treats native ETH as its own asset in there, so that can cause certain kinds of swaps to be cheaper. And it allows, and this is a sop to those who were really anti-JIT liquidity. And I was always against withdrawal fees, but you know what? In Hookland, we can allow anything. You can implement withdrawal fees that are charged on liquidity providers at the time they withdraw. So a hook can set that, and it can manage those and figure out who those are distributed to. So it really does open up a lot of range for creativity. I've seen some other cool stuff that I didn't have time to talk about here. But if you look in the Uniswap v4 white paper, you can see more details about what kind of hooks it provides. So now it's time for my second apology. So a lot of people like to talk about the end game of various things in crypto or on Ethereum or in decentralized exchange. And even I have fallen victim to this. I think I talked about a kind of teleology last year when I was on stage about how, oh, look at how coincidental it is that concentrated liquidity evolved from AMMs in the same way that central limit order books evolved. And look at how similar these things are. It's like how nature keeps trying to evolve a crab. We're all moving toward the same thing. And I think it's a bit tongue-in-cheek there, but I actually think it's important not to think in these terms, because I think there isn't just one possible future. There isn't one optimal endgame. There's this infinite game, because DEX is this inherently PvP metagame where every time you make some change, either to swapper behavior or to liquidity provider behavior or to just the rules of the game itself, it changes how every other party interacts. And now you have to go back in and you have to actually make another change in order to try to optimize something that you're trying to optimize for. And so, I don't think there is going to be an end game for decentralized exchange design. I hope there isn't. I actually think it's very interesting that we can keep iterating on this and finding new ways of designing exchanges and decentralized exchange. Cool, thanks everyone. Any questions?
Yeah, thanks for the talk. Please line up at the mic for questions.
Hi, so you have all these interesting hooks for the same pool. So for example, the same ETH pool could have multiple different hooks some having withdrawal fees, some not having withdrawal fees. How do you plan to manage the order routing for those?
Yeah, it's a great question. And I think the main answer to it is Uniswap X. Although I think there's a lot to be done in terms of Uniswap v4 specific routing infrastructure. And I know that the labs team is working a lot on that. But one way that Uniswap X, I think, helps is if you think about how on-chain arbitrage between AMMs work, it's an incredibly competitive and practically solved game. Where if you launch an AMM on-chain, and and you don't have good docs for it, you don't have an SDK, it's like you've got no front end, but you just like happen to launch an AMM into the void. Someone probably soon will start arbitraging it. It's sort of remarkable. And they'll arbitrage it against other on-chain liquidity. But what they won't do necessarily is route to it, because there's nothing that makes routing that competitive. People try, aggregators are trying, but there's nothing that makes it an incredibly competitive game where like anyone can make a lot of money every time they improve somebody's order flow. And Uniswap X is trying to import that competitive dynamic there. And so if you think about it in V4, potentially you could have a competition, and that's what Uniswap X provides. And again, didn't really talk much about X here, but is this competition to find what is the best actual path for this particular trade to go and put it there. And so that's what that is designed to solve.
Thank you.
So I have one that's both a question and an apology. You said your talk is not legal advice, but I'm going to ask for a legal question. So what's your take on the regulation concerns? SEC has opined that some exchanges, centralized or decentralized, are unregistered exchanges. Is there anything decentralization can help there?
Is there anything, I'm sorry, what's the question?
Is there, yeah, you can just share your thoughts.
Yeah. I think regulation is a really important thing in this space. I don't really have any particular comment on anything specifically. There was an interesting lawsuit actually that was dismissed this morning that was against Uniswap, a private lawsuit that I think had some interesting language in it about how the securities laws should apply to decentralized smart contracts, and I think that's pretty important. But generally, again, I think I try to leave that mostly to. I used to be a lawyer, but I'm a retired lawyer, so I try to leave that mostly to our very capable policy and legal teams.
Dan, I have a follow-up question on the previous questions. Basically, all the hooks, you can develop many interesting pools, but it's really at the mercy of the router side. I talked to Uniswap guys, like seeing about you're going to direct the traffic to the Uniswap X. But I just thought, like, if the fillers want to tap on-chain liquid to fill all the Uniswap orders, I personally think Uniswap X solved the MEV for the trader side, but my hunch is that every on-chain filler orders will be MEV'd because every filler will be profitable to fill. So I don't know how you guys thinking about that, because otherwise you don't have a market to even achieve the Uniswap X market when you even started, right, for field.
Yeah, I think in general the goal is to make the competition so close to perfect competition, such a competitive process that the arbitrage profits or filler profits in general are pushed down to epsilon. I think that's generally the goal of designing these things. I definitely don't think anything here is there yet, but that's ultimately the direction I think we're trying to push in this game.
I'm not trying to talk arbitrage in this case. It's really about the MEV attack the fillers, because filler did all the research, figure out the filler that's going to make money out of fill. I don't need to do the work. I just copy off the transactions, and there's a front run. You basically make money out of that.
Yeah, and again, I think the goal of the design here is to make put fillers in such a competitive position that actually there's no edge there. And so ultimately they have to provide basically the best price possible minus epsilon. And again, I don't think anything is there yet. I'm not sure anything ever will get there again. I think there is this infinite game where if we find some solution that does well enough currently, potentially people can change the behavior. But like I think that's the goal that we're trying to do, is make it as competitive as possible so there isn't as much profit that goes to MEV or to sophisticated.
Yeah, but if there's no profit for the fillers, what's in it for filler to do the job, to fill the transaction, because pool is all passive, waiting for the filler to fill the orders, because the router your routing is not routing to the pool, it's routing to the
Yeah.
Kubernetes account.
I think it is a really interesting question. I do think in the long run, there are interesting ways to make passive liquidity still competitive on this. But we'll have to talk about it offline because I think I'm out of time.
Yeah. Thank you, Dan.
Thanks
again.
so much for having me.
We're out of time. We'll move on to the next talk. Our next speaker. Our next speaker is Stefanos. Stefanos is a PhD student from Imperial College London, working with Professor Ben Lifshitz. And he will tell us about smart contract and DeFi security insights from two evaluations and practitioner surveys.
Thanks for the introduction. So today I'm going to present a joint work with colleagues from Imperial College London, the University of Athens, and UCL. So the previous talk was a great example of all the progress we have in the ecosystem in decentralized applications, but also we have seen tremendous progress in developer tools, in security tools. Also, we are trying to scaling the whole ecosystem, both DeFi, but also basically any blockchain with smart contract capabilities. But in all of that, there is a constant, and that constant is attacks. It doesn't matter if it's 2021, 2022, 2023. Anytime you check DeFi news and in general blockchain news, you see a new attack. So the solution to that has been auditing, and auditing I think is an industry standard at the moment, but we also have spent much effort into developing security tools. We have developed static analysis tools. We have done a lot of research into developing better analysis techniques. We have worked into symbolic execution tools and practical symbolic execution tools for analyzing smart contracts. There is amazing work into formal verification for smart contracts and DeFi applications, and also a lot of work into fuzzing. So we did a survey, and we detected 76 security tools for DeFi, and this is not a complete list. I'm pretty sure there are much more tools out there, and if we also count all the proprietary tools, then I'm sure it's more than 100 tools developed in the last years. And that doesn't change much in practice. This is a figure from DeFi Llama, and it depicts all the losses from attacks since January 2023. And the sum is pretty mind-blowing, because after all that research, we still have a lot of attacks with a sum of 691 million. And there might be some white hat attacks there, and there might be some attacks missing from that data set, but still, that's a lot. So our question is, what is the practical impact of automated security tools in practice? Because in any new scientific paper, when we go to the evaluation part, we see like very few false negatives, and also a pretty high precision for all those tools. So we wanted to evaluate it, especially automated security tools, which is the main focus of research, to evaluate their usage and their effectiveness in practice. So there is a paper from last year that was also presented here, an SOK on DeFi attacks. And that paper contains a pretty nice data set that includes 181 DeFi attacks with losses of more than 3 billion USD from 2018 to 2022. And it's a nice data set because it contains a lot of information about the attacks, what is the vulnerability that was exploited, which were the contracts that were attacked, which addresses performed the attack, and really fine-grained information. So that's a great data set, and specifically for attacks in the smart contract and in the protocol layer, it contains 127 attacks. And this is what we used. for evaluating some tools, but we also want to select some of the tools. And we saw that there are 76 tools in our survey, but after applying some criteria, and more specifically, we wanted the tools to be open source, to be automated, meaning that there is no need for user input, and also we want to be maintained. And surprisingly, that leads us to only 7 tools, and we selected 1 tool per the 4 main categories. The first one is Solheim, which is a linter, and we don't expect linters to detect critical security vulnerabilities, but still it's a tool that many people use, so we include that. We also selected Slither, which is a static analysis tool. We selected one of the most well-known symbolic execution tools in the space. Unfortunately, for fuzzing, we selected academic tool because no other fuzzer that was automated, meaning there's no need for user input, was available at the time. I think in the last 6 months, 2 really good fuzzers has been published, and they are open sourced. And also, we selected a tool called Oriente. How many here know that tool? So, very few people. So we selected that tool because it's one of the first tools in the space from 2016. And what's interesting is in paper evaluations, people still evaluate their tools against Oriente. Oriente was developed in 2016, so our hypothesis is that it won't be effective. And we want to validate that hypothesis. So here is the table with all the vulnerabilities in the dataset. The layer of each vulnerability, and also the number of vulnerabilities and the number of attacks that exploited such vulnerabilities. And also we have the tools and the automated tools, and which vulnerabilities those tools support. And important finding here, not finding but observation, is that the top 2 categories cannot be handled by the selected tools, and that's across most of the automated security tools. And that's kind of expected because, for example, the first category, it's absence of coding logic or sanity checks, which means that you actually need some input to know what is the expected logic for the smart contract. So the total dataset is of 127 attacks. The tools we selected can potentially detect 32 of them, and also the rest are out of the scope of those tools. So we wanted to evaluate those 5 tools into those 32 attacks, which is still a pretty big sum of funds lost. So how we do that? We have the dataset, we have the security tools, and from the dataset, we extract the vulnerable contracts. We also developed some tooling here to go from the proxy to the actual contract that was executed at the time of the attack. And then we use Smartbugs. Smartbugs is a tool for running other security tools. And the way it works, you provide the contract and you run the Smartbug, and Smartbugs will run all the tools you have selected, and you will get some results. We perform some post-processing steps to clean up our data, and in the end, we again used the dataset. For each contract, we found like what was the vulnerability that was exploited for the attack, and we checked if any of the selected tools actually found that vulnerability. And for every positive result, we also manually verified that those are indeed true positives and not false positives. And here are our results. So 11 of the attacks in this dataset, summing up to 150 million in losses, could have been detected and potentially prevented if at least those really simply to use tools, again, this is tools that do not require any user input, just run them. And in our setup, also, it's a bit unfair to the symbolic execution and the fuzzing tools because we didn't fine-tune how to run them, which is important to do for such tools. But still, 11 tools, 11 attacks could have been predicted. And what's interesting is that all of those vulnerabilities were reentrances. And for me, that's a positive finding because most of the research since 2016 has been into detecting reinforced vulnerabilities. And I'm pretty sure if we used proprietary tools from some of the security companies, then definitely all of the 13 reentrances would have been detected. So the point here is that it's really, really important to actually use these tools and to actually assess the results, even if there are some false positives, and a lot of funds can be saved. A second point is that automated tools, because of their nature, can only detect some vulnerabilities. Maybe in the future we will have some more advanced techniques that will enable us to detect more kind of vulnerabilities with automated tools, but currently we are focused on only very specific vulnerabilities. And more research needs to be done to extend the number of vulnerabilities that those tools can support. Also, what we already mentioned, that a non-negligible amount could have been saved if those tools were used. And another point, it's more on people that are developing tools and evaluating them in research papers, but also in their benchmarks, to not only use synthetic benchmarks, but also try to get some real-world contracts and evaluate your tools in those contracts, because that's how the users are going to use them in the end. And last point here is that semi-automated tools, such as invariant fuzzers and formal verification tools, could have been prevented more than 47 attacks if the specification or the invariants were correct and the tools are correct. And again, I think that, okay, in formal verification, there's a lot of research, but formal verification, it's kind of hard to do. So I think more research needs to spend to semi-automated tools, and that might not be the most fancy thing to do in academia, but still could have a great impact in the industry. And there is also a pretty nice repository from Antonio if you want to check more about invariant fuzzers. He's trying to evaluate two of the most prominent invariant fuzzers. So, next, we want to see how actually developers and auditors use your tools and if the tools are actually useful in practice, or it's something that we are doing in research. We develop cool tools, potentially with nice results, but people eventually, for some reason, do not use them because we still have a lot of attacks. And for doing that, we performed some surveys in 27 developers from top DeFi protocols replied our surveys, and also 22 auditors from security companies, but also independent auditors. And here are some of the demographics of the auditors and the developers, and we have a range from low seniority to more senior people, and also most of them are working mainly on Ethereum, but also other EVM chains. So let's discuss a bit the familiarity and usage of security tools in practice. So the first figure is about experience with different tool categories from auditors and developers. And we can see, for example, that developers' toolkits, such as Foundry, Hardhat, are some of the most used tools in practice. And that's an important point because when you develop a tool, it's a good idea to try to integrate it with those frameworks. And I think one very good example here is the Foundry Fuzzer, which works on top of Foundry. And I think that's a way to have better adoption of your tooling in practice. Also, another point is that static analysis and symbolic execution tools are heavily used by auditors. And also other tools such as IDs and litters are used by developers, but I don't know how much security benefits we can get there. And next, we have some specific tools, and we ask developers and auditors to select which tools are used in their organizations. And here are the results. And some findings here are that developers in general prefer lightweight tools. They want to have results pretty quick because while they're developing, they want to have some feedback on how secure is their code. On Another note is that academic tools that, again, are frequently appear in paper evaluations are not used in practice. Those examples could be Securify, Mayan, and Rion. They are pretty outdated, but still used in many evaluations, which we think should change, and we should evaluate our tools against the state of the art, and if state of the art is not available, the state of the practice, which is tools such as Slither. And then a large amount of both developers and auditors actually use tools that could have revealed logic-related bugs, such as for-form verification tools and invariant fuzzers, which is another important aspect. And again, more research needs to be spent there, and in tools that can help actually use that tools. For example, some tooling for helping with specifications, etc. Next, the majority of auditors spend up to 20% of their time using security tools during audits, which is still high because auditing is mainly a manual effort, and it seems like auditors actually want to use those tools and try to use them. Next, we want to identify what are the things that make security tools valuable. And we asked both developers and auditors to say how important is the report quality of the tools, the documentation, the ease of use, the false positive and the false negative rates. And what we can see from that is that in contrast to academic work where precision is really, really important, low false positives can be okay, especially if the tool provides some value to the users. And value, we mean the ability to identify vulnerabilities that could lead to a lot, to severe losses when the smart contract will be deployed. And another point here is that auditors mainly emphasize the importance of tool setup and bug finding capabilities. And this is expected because an auditor has only a very specific time frame to audit a contract, so he doesn't want to spend like one day trying to set up a tool. On the other hand, developers emphasize the ease of integration into their development life cycles because they want to use the tools daily. So an important takeaway from here is that probably when you are developing a tool, you should ask yourself who is the target user for that tool. And if the answer is developers, then probably you want to focus on different things. And if the answer is auditors, then some other things are more important. Secondly, we also asked which vulnerabilities are the most difficult to identify manually. And not surprisingly, the top categories from our dataset, it's also the top categories in the survey results, which is logic errors, oracle manipulation, and absence of coding logic. And then we asked for which of these vulnerabilities you think there is limited support for existing tooling, and the answers were pretty similar. So I think that we need, as researchers, to definitely focus more in tooling for detecting logic-related bugs and oracle manipulation vulnerabilities, but also some other categories that are under research at the moment. And also, another important finding is that almost 40% of the auditors do not find security tools useful. So this is also something that we should improve. So what should be the main takeaways for all this work are three pretty simple things. Firstly, automated security tools can't prevent important vulnerability classes and should be used. And it's really a shame if we don't use those tools. Secondly, security tools should focus on detecting more vulnerabilities. We have done a pretty decent work into detecting reentrancy, and we still need to focusing on reentrancy because there are new classes of reentrancy that can happen. But we should also focus in other vulnerabilities. For example, on-chain oracle manipulation is a vulnerability that needs more tooling, and recently there are some works towards that way, but we need more. And finally, I really think that researchers should focus more on improving semi-automated tools. And again, there's a lot of work for full memory verification, but also I think like something in between, like invariant fuzzers, it's something that we should focus. And we should also focus on other tooling that can help using such security tools. So that was my presentation, and here you can find our paper, and in a few days we're also going to release the dataset and the code for that work. Thanks a lot.
Let's go ahead.
Hey, so I have a quick question about one of the slides you showed about the target blockchains. I think like an emerging attack surface area is the like minute discrepancies between the target VMs that people are writing these programs for, and just wondering how you think the tools should accommodate like different target architectures.
So you mean, for example, blockchains where you write contracts in Solidity and Cairo, or different, different versions of EVM?
Practical example is like the OP EVM not having the push zero opcode.
Mm-hmm. Yeah, that's a really interesting question. And I think we need more empirical data on what exactly are the differences and what is the impact. And basically, we need some tooling to be able to identify those issues before deployment.
Yeah, please.
Hi. Thank you for presentation. So I have a question about the how to find the vulnerability of sense of coding logic of sanity check and also like on-chain Oracle manipulation, because according to the table you showed at presentation, the both two type of vulnerability was not able to detect it by all tools. And actually, I'm doing some auditing so far, and both two stuff was mostly should be found by the manual checking by the specific auditors who have enough experience and knowledge. Do you have any ideas to detect that both mostly the on-chain Oracle manipulation of those vulnerability by the tools, or do you have any idea to make it automated?
Yeah. So regarding the absence of coding logic and the logic errors in general, I think formal verification tools and invariant fuzzers are great tools to use in order to detect such vulnerabilities. And for on-chain Oracle manipulation, I don't think we have something, at least open source at the moment. I think there are a couple of papers that have been published in the past year that they try to automatically detect such attacks, but currently we don't have something for that. So it's mainly a manual effort to detect those bugs.
Thank you so much.
Thank you for your presentation. Curious about your so-called automated tool. So actually, I'm a developer first. So actually, traditional computer, we don't use too many tools for prevent attack, especially for security. For example, I have a Mac or Windows operating system, so it can prevent the prevent the attack initially, naturally. But I just wonder if one day maybe blockchain, because now all your research are in EVM blockchain, so maybe like EVM itself is not that secure. So as an operating system, it cannot support kind of security. So like how do you view kind of tool and also like from the virtual machine level security?
So the question is, what if the underlying infrastructure is not secure?
Yes. So some developer, some computing system, they support security directly. Don't need any like tools. We need to integrate them.
If I understand correctly, the question is what we can do in EVM to reduce the possibility of introducing bugs in smart contract by developers.
Yeah. So we just think like as a developer, we shouldn't integrate too many tools, but instead like they should provide us like a good environment so we can develop.
Okay. So the question is basically if we can somehow perform EVM hardening, right?
Yeah.
So to have, for example, to disable reentrancy from happening in general.
Yeah,
Okay,
yeah.
okay. There are a few papers into that on how we could potentially perform EVM hardening, but that needs changes to the EVM itself. And I think at least for L1, it's pretty difficult to do such changes. But probably some of the L2s might actually want to introduce such changes and provide a safer environment for the users.
Thank you.
Sure. Thanks for the introduction of the overview of the secure tools, really important. I do see there's some of the discussion right now in the industry that we can do more than just secure tools. For example, in the traditional software industry, we're doing the unit test, integration test, system level test before we GA our products, right? Right now, what I see is the secure tool is just like unit test level kind of thing, but there's a lack of more like in-depth of integration and system level testing. What's your opinion about that? This is number one, question number one. Number two is, are you aware of any of the open source or framework doing that sort of integration and system level testing?
Mm-hmm. Yeah, that's a great question. And I think in the past few years, there is a lot of development towards that end. I definitely think that more testing needs to be performed. But also when you have such testing infrastructure, it's also pretty easy then to have a fuzzer that uses those tests to perform even better testing. So that's one point. And what was the second?
Same question is any of the aware of any framework or open source that doing such a
I think both Foundry and Hardhat are great choices for that.
Okay, but you mentioned just fuzzing. Fuzzing is just one aspect of it. We have a lot of things, because a lot of things, if you're looking at the recent attack, our Flashloan attack, our attack, is not because of the code has any of the attacks, right? It is because of when there's some Flashloan attack, for example, they manipulate the offline oracle, then make the price to be like down and up and trigger such attack. How do you take care of that? The secure tool itself cannot detect such scenarios, right?
Yeah, in some sense. One option will be like to have an environment that you can run such tests, and you have, for example, a Flashloan provider in your environment. They have some test infrastructure using that and try to break your application in that sense. And other solutions, kind of the main solutions, is runtime monitoring, right? Where there are a few recent works that trying to detect vulnerabilities on chain from the mempool before happening and try to front run them so they can defend against such attacks. So that's another option.
Okay, last follow-up question. When you say our tools need to be more developer-friendly, are you mean that tools need to open some API that developer can directly call instead of like manually integrate them? Is that what you refer to?
I think in general, it should be easier for developers to run the tools, and that has multiple layers, right? Better documentation, easier installation, or more examples on how to use properly these tools, etc.
Okay, cool. Thank you very much.
Let's thank Stephanus again. Our next speaker is Kushal Babel. Kushal is a PhD student at Cornell Tech, working with Professor Ari Jules, and he will tell us about measuring the economic security of smart contracts using adaptive learning.
Is that okay? All right. Check. Okay. Thank you, Ling, for the introduction. So now I'm going to talk about our work titled Lantern, Measuring Cryptoeconomic Smart Contract Security Through Learning. And this is joint work with Mojan, Mahimna, Yan, Farinaz, and Ari Jules. And by the way, this work is also going to appear at CCS later this year. Before I start my work, I'm very happy that Stephanus's talk and all the questions have set a very good stage for this presentation. So as we've seen, smart contract security is in a stage where multi-million-dollar hacks do not even make the news anymore. But really, why are these hacks so commonplace? Well, one of the reasons is that the interactions between the underlying smart contracts is quite complex. And these smart contracts can also interoperate very easily. So for example, you can have lending contracts that use decentralized exchanges as oracles. You can compose multiple decentralized exchanges together so that you have arbitrage-like opportunities. And of course, flash loans wreck the cryptoeconomic behavior of all the other contracts. And the second thing that makes it quite challenging is this notion of MEV, right? Where the miners or the validators can reorder users' transactions or insert new transactions to extract value from them. Now, for the purposes of this talk, it's important to note that MEV can be used as the measure of cryptoeconomic smart contract security because in some sense, validators are kind of the most privileged actors in the ecosystem. And so if you actually measure the MEV in the system, you get a good idea of what's the cryptoeconomic security of these smart contracts. All right, so now here's the outline of the rest of the talk. I'm just going to briefly touch upon the previous approaches a little bit. Then I'm going to present Lantern, the overview of Lantern, some details about the design, evaluations on real-world data and contracts, some limitations, and finally conclusion. All right. So the previous approaches can be categorized into two broad categories, in my opinion. The first category is what I call heuristics-based. So these works basically encode a particular attack strategy, and they're essentially looking for patterns in the transaction data or the blockchain state. Now, these strategies, or these approaches rather, are very efficient at finding these simple attack strategies like arbitrages, sandwiching, and so on, but they do not generalize to new contracts or new kinds of attacks that you might see. So as a result, they do not attempt to find the worst case behavior or the worst case adversarial advantage in a given set of contracts. The second category of approaches is based on formal verification, one example of which is Clockwork Finance, which I also presented last year at SBC. So these approaches actually leverage formal verification to, in some sense, characterize the optimal advantage that an adversary can have by either inserting or reordering transactions. They also provide formal guarantees to what the maximum MEV can be. But as you might expect, these approaches are not very scalable on two dimensions. The first dimension being that if the contract is too complex for the verification to happen, so if the contract like, say, Curve Finance or Uniswap v3, which have loops, program analysis becomes a little bit tricky. You have to manually specify loop invariants and so on. Or if there are a large number of transactions, then the search space explodes quite a bit for tools that are based on symbolic execution. So just to summarize these two approaches, one is heuristic-based approach, which is efficient but not generalizable. The second one, formal methods-based, which is generalizable but not very scalable. Lantern actually bridges this gap. So Lantern is a generic and scalable tool that finds MEV opportunities so that we can understand the economic security of the contracts better, and also the compositions of these contracts. So now I'll present the properties of Lantern first, and then we'll see the design and evaluations later. So the first property that I already mentioned is generalizability. You don't need to encode specific attack strategies like even arbitrages, sandwiches, and so on. You really treat the black box, you really treat the smart contract execution as a black box environment. There's a slight caveat here that you require some templates, which I'll touch upon in a bit. You require these templates for a contract to guide how the insertions can happen for that contract. The second one is that it has native smart contract execution in the sense that we are not really translating the smart contract to some other representation, some other model, or so on. So the output of Lantern can actually be directly executed on-chain as it is. Third one is scalability. So as I already mentioned, if the contract is more complex, we are not doing any program analysis. So if the contract has loops or other things, it doesn't really matter for the simulation, as long as the concrete execution time is small. And we can deal with larger number of transactions, so more than 50 transactions in a strategy. That's quite a lot of permutations, but if there are more than 50 transactions, that's still okay. More than 10 insertions, that's still doable. And finally, in practice, this property is quite useful, which is the adaptability to computational budget. So if you have more computational budget, you can leave Lantern on running for longer, and it will keep on finding higher and higher MEV values. If you have smaller budget, you can terminate the program early, and you'll get the result up to that point. And finally, it's amenable to parallelization. I'll talk a little bit more about that later. But you can actually parallelize Lantern across multiple servers because you can do parallel simulations. OK, so next on to applications. As Stephanus reminded us that tool developers should think about who are the users of their tools. So developers and researchers can actually use Lantern directly to study the crypto economics of their contracts. And they're also in a good position because, as I will mention, it's required to specify some templates for these contracts. So developers and researchers are the ideal customers of Lantern. Users can also use Lantern if they want to understand how much value can be extracted from their transactions. And while we do not intend to promote this, strategic agents can also use Lantern to extract value from user transactions. Real-time usage of Lantern requires more parallelization than we currently have, but I can talk about that offline if people are interested. All right, so now let's dive into the details. Let's see what the problem overview is first. So given a set of user transactions and the current blockchain state, Lantern wants to automatically learn to maximize the EV from these transactions. So what are the various actions that Lantern can take? Well, it can reorder these transactions, or it can insert new transactions of its own. Now, for the second part of the question, where it inserts its own transaction, we guide the insertion using some templates. So templates can look something like this, where for an AMM, the template could be swap alpha naught token 0 with alpha 1 token 1, where alpha 0 and alpha 1 are the variables of the optimization. So Lantern will optimize these variables. Token 0, token 1 are the tokens that the users are trading in. So alpha 0, alpha 1 are like the template variables of this optimization problem. All right. So the overview or the architecture of the tool is basically it comprises of two components. The first component is the learning-based module, and the second one is the simulation environment. Both of them work in concert in the sense that the learning-based optimization module will ask the simulation environment to give feedback about whatever it's trying to do. So it will actually give a concrete transaction sequence for the simulation environment to simulate. The simulation environment would report back what is the EV that the validator obtains in this particular transaction sequence, and then the learning environment will actually update its internal structures. All right. So let's take a deeper look inside the learning module. The inputs, as I said, are the transactions and the block height at which you want to analyze these transactions. And you also have the templates for validator inserted transactions. And the output of the learning module at the end of all the iterations and feedback with the simulation environment would basically be how much MEV the learning module has been able to find, and what is the sequence of concrete transactions that you can execute on chain to get this MEV. So there are two loops in this learning module. If you ignore the figure, that's OK. The main takeaway from this figure is basically there are two nested loops. The outer loop actually optimizes the ordering of transactions, and the inner loop optimizes the template variables or the variables inside the transactions. So you first try to figure out what's the right order, and then in that order, you kind of optimize the variables for that particular transaction sequence. So to be more precise here, what we are trying to do is optimize this function f, which is the validator's EV in terms of ETH. Or any other native currency. And the vector that we are trying to optimize over is the design variables, which is composed of two things, the ordering and the variable values inside the transactions. And we formulate it as a bi-level optimization, as I mentioned, so that we have these two nested loops inside the learning module. And finally, we also provide the bounds for this optimization. So these bounds kind of define the search space. So for example, for the ordering, the search space would be set of all permutations, except for you can't reorder same user's transaction because these transactions contain nonces. So except for reordering same particular user's multiple transactions, you can explore all the possible permutations. And the other search space for the other variables is basically defined from the type of that variable. So if the variable is, say, int24, uint24, the search space would be 0 to 2 to the power 24, and so on. Okay. So the goal is to empirically search for the optimal vector that maximizes this function, which is the validator's EV. Now, we are empirically searching for this because we don't know of any analytical solution that will optimize this. And therefore, we rely on accurate simulations of EV for various samples. Now, some notes about search. As you might have already guessed, the search space is huge. Even for this small toy problem that you see on the bottom right, there are just 4 transactions, 2 user transactions, and 2 transaction insertions from the miner or the validator. And the range is also relatively small, but you have more than 30 billion possibilities here. So the idea is that the search should converge fast, it should be efficient, and also it's good if it's parallelizable. And just some ideas about the search space geometry. In general, we are dealing with smart contracts, which are Turing-complete programs. And so the search space can be non-monotonic, non-convex. The variables that we are dealing with can have high correlations between them in the sense that if you have 2 variables in your transaction providing X token and Y token for liquidity, they are really correlated. You can't provide them independently. And in general, this is a very high-dimensional search space. So this particular illustration is for a problem where you're trying to provide liquidity with respect to 2 tokens. The 2 tokens are on the X and Y axis. The Z axis is the EV that you get by providing these tokens. All right. So the algorithm is quite simple. And this is the high-level sketch. I'd encourage you to look at the paper for a detailed algorithm. But the high-level sketch is very, very simple. What you do is basically you initialize a random distribution. You iterate up to n iterations. And in each iteration, you just sample from the distribution. Okay? And then you find what's the EV for this sample, the maximum EV. You update your EV. And you identify what are the good samples in this particular batch of samples. And then you update your distribution to be a little bit biased towards the good samples. So you're basically iterating over your distribution and trying to focus on the more good samples. The paper has more details about how you don't get stuck in a local minima, how do you kind of also transport away from these local minimas and so on, or rather local maximas. But the rough sketch is something like this. All right. So now I'll talk a little bit about the simulation module, which is the second component of Lantern. So the learning module provides these concrete samples of transaction sequences, which you can simulate. And so the simulation module's job is to just simulate this concrete transaction sequence. So it basically receives the block height h at which it wants to simulate. We set up some initial things like approvals for contracts and so on. And we give the validator some initial capital. So for our experiments, we have various different categories of capitals. Like if you are doing liquidity provision, you need to provide a little bit higher capital to get meaningful results and so on. But we give it some initial capital. And then we simply execute the set of transactions. At the end of the transaction sequence, you might have ETH or some other non-native currency. And in order to get a scalar value of EV according to our definitions, you want to convert the non-native currencies like USDC or other currencies back to ETH. And so for that, we use either you can settle on the decentralized exchanges, or we use historical prices from centralized exchanges. The assumption being there is no slippage on the centralized exchange, and so you can directly use the price to convert the tokens into ETH. And then you give the EV that the validator has at the end of it back to the learning module. All right. So now on to evaluation. We conducted our evaluations on these 3 biggest AMMs, Uniswap v3, Uniswap v2, SushiSwap, and one of the biggest lending protocols, Aave. For the dataset, we basically filtered the blocks that are likely to have MEV opportunities. So for SushiSwap or Uniswap v2, we filtered blocks that have more than 500 ETH transactions, or 1,000 ETH transactions on Uniswap v3, because that gives us a manageable data set size. Otherwise, the data set gets too huge. For centralized exchange prices, there are freely available data sets from Binance for historical minute-level price data. And as you will see, there is also a baseline in the experiments. So for the baseline, we use the free data from Flashbots API, which basically gives you the bribes that are being paid by searchers or bots for each of their bundles. So this is just for us to get a perspective on how much MEV Lantern is uncovering with respect to that context. And finally, we also need to provide template transactions. So for the given contracts, we provide template transactions for swapping, for liquidity provision, and for liquidation on Aave. Right. So now let's look at some evaluation graphs. So this particular graph shows the MEV uncovered by Lantern on Uniswap v2 in isolation, just trading on Uniswap v2. The orange line is the baseline that I talked about, which is the value that's being extracted by strategic agents in the wild. We don't have the data for how much value they are extracting, but we have the data for how much bribes they are paying, and we think that's a good enough tight lower bound for the value that they might be extracting. Note that in this graph is not, the orange line is not meant for strict comparison because Lantern also has, looking back, it also has the data for the bots transactions, and it's also reordering the bots transactions. So the orange line is just for the context of how much MEV is being uncovered by Lantern. And so we observe Lantern, of course, discovers the well-known strategies, front-running, sandwiching, to extract this MEV. But interestingly, it also discovers new strategies. So now I'll go over two of these new strategies. So the first one is what we call Lazarus strategy, which basically involves bringing a dead transaction back to life. So one example for this is this particular transaction, which was done by an MEV bot. This transaction was dealing with Uniswap v3, but for whatever reason, this transaction failed. Maybe the MEV bot had some strict requirements for profits from that transaction or whatever, but this transaction failed. Now what Lantern did is basically reordered this transaction so that this transaction actually succeeds, but then it front runs the transaction by inserting a transaction before this one. The second strategy that I want to talk about is what we call gas leaching strategy. So MEV bots usually have safeguards in their transactions. So some of the safeguards could be like, if I don't have profits of over more than $5, then don't do this transaction, just revert. And they also expect their transactions, some of them expect their transactions to be ordered right at the top of the block or wherever Flashbots is guaranteeing them to be, at least before MEV boost. But some MEV bots don't have the safeguard in their transactions, as we noticed. So some of these transactions, at least from some bots, of course, these transactions pay a very high gas fees because these are, after all, from MEV bots, and they want to win the auction. So they pay a high gas fees, but if you reorder them slightly, they just run into an infinite loop, and they consume all the 15 million gas in the block, and as a result, you get a very fat transaction fees for the validator. Of note is this particular bot that pushed a lot of numbers in our results. But this particular bot is not like a naive bot or a new bot. It has like more than 300,000 transactions on chain. And this bot's transactions can actually run into infinite loop if you reorder them slightly. Then we also went on to Uniswap v3. As I pointed out, Uniswap v3 is a little bit more complex. So we don't incur the penalties of program analysis on Uniswap v3 and so on. We just do simulations. And so we see Lantern also does well on Uniswap v3. It also executes the similar strategies on v3. And then all these graphs so far were concerned about just trading, where we only provided the templates for trading on Uniswap. Now we also provided templates for provisioning of liquidity on Uniswap v3. And some of you might know that provision of liquidity on Uniswap v3 is a little bit tricky, where you also have to specify the ranges in which you want to provide liquidity, and that really affects your profits and losses. So it's a good field to test your optimizations. So for v3, the way to interpret this graph is basically, this is the difference between if you provide the liquidity abilities for the liquidity provision abilities to the validator versus if you don't and you're simply doing trading. So if you add the liquidity providing templates to Uniswap v3, then we see that you can extract more MEV just from providing liquidity. And so these strategies are commonly called just-in-time liquidity strategies, where you can actually just provide liquidity and remove it immediately, and you extract some profit as a result. Then we also did compositions of different AMMs. And we see that if you compose AMMs, you of course extract higher MEV than if you were not composing them. And this additional profit, of course, comes because of arbitrage. Now, moving away from AMMs, also for lending contracts, it's important to see if Lantern can generalize beyond AMMs. And so for lending contracts, we composed Aave with 2 other AMMs, SushiSwap and Uniswap v3. So SushiSwap and Uniswap v3 basically provide the validator with the capital to actually go and liquidate positions on Aave. And we controlled this experiment for only isolating the profit from liquidations and not AMM activities. So this graph shows that from liquidations, Lantern can also uncover significant MEV. Now, these were the graphs for how much MEV you are uncovering. But now I want to talk about what's the execution time for Lantern. So we conducted our experiments on a single server, 48 CPU threads, 24-core server, 128 gig RAM. And we did 44 parallel simulations. So as I talked about parallelization of Lantern earlier, you are evaluating a bunch of samples in each iteration. And you can actually evaluate those samples independently on different simulation environments. So we instantiate 44 parallel simulation environments and see the running time for Lantern. The way to interpret this graph is the various lines are different quartiles of problems. So the green line is representing the 50th percentile of the problem. And the y-axis is how much percentile of MEV, how much percentile of the eventual MEV that Lantern would uncover, how much percentile of that it is uncovering as a fraction as time goes on. So as time goes on, how much quickly you converge to your final value. And so the green line shows that for more than 50% of the problems, you uncover 100% or close to 100% of your MEV in less than 100 seconds. Okay, so moving towards limitations of learning-based tools. The first one is you need some mild regularity conditions on your smart contract behavior for learning to actually be successful. So if you have these cryptoeconomic attacks where just on one particular value of a variable, like we saw in some of the bridge hacks where you need just one particular value for the attack to succeed, like some initialization value or so on, some null values. That would be a single spike where the MEV spikes and otherwise it's 0. And so those kind of search spaces are not really amenable for learning. The second one is it requires manual specification of templates. But as we saw from the previous talk, maybe that's not too bad. Developers and auditors anyways want some manual controls. And we think that's these templates are not really a big deal in practice for developers. So in conclusion, we formulated the problem of cryptoeconomic security as a learning task. We proposed a learning algorithm for it. And the approach can generalize to any smart contract because we really treat the smart contract as black box execution environments. And the output as a result can be executed directly as is on chain. And we saw that Lantern is scalable and it uncovers significant MEV compared to what the MEV that's being extracted in the wild. And I would encourage you to go look at the paper and the code on GitHub. And I'm happy to take questions.
We have time for a couple of questions. Please.
Hey, thanks. It's a really good presentation. First question I have is you mentioned that to reach the quick converge, we need to have select the good samples. What's the algorithm that you can select the good sample out of the billions of combination of possibility scenario?
Right. So the criteria for good samples is just how close the evaluation of sample is to the maximum. So if you have 100 samples, evaluate the EV on all those 100 samples. These are concrete samples, so you can actually send it to the simulation environment, get the EV back. So the max, whatever is the max sample, you see what are all the other samples that are pretty high compared to the max. So you basically take the top layer, and those are your good samples. And then you update your distribution to be around those good samples.
Okay, thanks. Second question is about the how developer going to use the Lantern. For example, I have a smart contract, right? How I going to use it? You mentioned there are some limitations. Do I need to do some insert? Do I need to do some modularization of my smart contract? What's just a high-level procedure? How do we, given a smart contract, how are going to use the Lantern?
Right. So I guess there are maybe three things that you would need. One is just the address of the contract that you want to analyze, either the mainnet address or if it's deployed on your local DevNet. The ABI of the contract. And the third thing is you need to specify some templates for insertions on that. So when we added Aave to our experiments, we just gave the Aave address, the lending pool address, and then we gave just one template for being able to liquidate. So there's a liquidation call in Aave. So you just say liquidation call, the signature of the function, and that's pretty much it.
I see. Last question.
I suggest we give others a chance to ask questions.
All right. Appreciate your help. Thank you.
Yeah, we can talk offline.
We still have time, yeah.
So, great presentation. I'm trying to understand your baseline. You said that the baseline is pre-MEV boost payment to validators, right?
Right.
But that means that because your optimization problem also has in there the choosing how much to swap, you're effectively not just a block builder, you're also an MEV searcher. You're searching for opportunities. So your baseline does not include the actual gains of MEV searchers, like the whole hundreds of bots out there that try to get MEV. They don't get all their profits to the validator. They're trying to give to the validator as little as possible.
Right.
But because of competition, sometimes they have to give like maybe more than half their profits. So your baseline does not include all the gains of the bots, right? So in practice, you're probably not that far from reality.
Right. So as I mentioned, the baseline only consists of the bribes that are being paid to the validator. So whatever the searcher is giving to the validator. The number there is not really more than half. The number is actually more than 90 to 95%. So if you look at most of the transactions that these searchers are doing, more than 95%, even before MEV Boost, say 2021 or 2022, more than 95% of profits in most of the transactions were being paid as bribes.
Well, that's misleading, though. You're right. In most of the transactions, more than 95% of the profits go to the validator. But if you take the whole volume of money, there are a few highly profitable transactions at which MEV bots make a ton of money, and only 20% goes to the validator or something. That's MEV bots make their money out of the transactions that no other bots get. And the validator gets a little bit of the payment in those. So if you actually see the EigenPhi statistics, they were recently presented at like trade conferences. It's not more than 95% that goes to the validator. It's actually about, if I remember correctly, like for the month of June or July, 20/80. So 20% goes to MEV searchers now. 80% goes to the validator, and now it's much more competition than like block 14 million. So back then, probably it was 40/60 or something like that is my guess. That's why I'm saying that your baseline is probably a little skewed.
So 2 points. One is we think that that's the most accurate baseline that we can have without actually going into what their off-chain mechanics are, where they're selling on centralized exchanges, how much profits they're actually making, because that's really hard to determine. Unless they are doing some very simple trades like cyclic arbitrages. So that's the first point. The second one is we should discuss more about the numbers, but I think my recollection is even before around 14 million blocks, we actually examined most of the transactions ourselves and calculated the profits in which we could, and it was around 90%. But we should check the numbers again. But yeah, this is the best line we could come up with.
Yeah. One last quick question.
Hi, thank you for the talk. Could you repeat what learning strategies you used to learn parameters like alpha 1 and alpha 2?
So the learning algorithm is like a simple iterative algorithm that just samples from the current distribution, and what you're trying to do is basically arrive at a distribution that gives you good samples for alpha 0 and alpha 1. So if, say, alpha 0 was the optimal values around 10, you want to bias your distribution to around 10 rather than a uniform distribution.
Oh, okay. So you're randomly choosing samples and
right, and then evaluating them and then updating your biases.
I see. Thanks. Okay. Thanks.
Yeah, thank you, Kushal, again, for your presentation. Okay. Our last speaker for the session is Itai Tsubari from Technion. And he will tell us about Ledger Hedger gas reservation for smart contract security.
Hi, good afternoon or noon. Thanks for having me. My name is Itai. I work at Starkware, but I'll present a work from my time at the Technion. The title of the work is Ledger Hedger gas reservation for smart contract security. As we all know, there are many smart contract applications that require timely confirmation of their transactions. And their entire security relies on that. However, transaction confirmation times can be volatile, which result in security concerns for these applications. So in this work, we present Ledger Hedger, a contract for a timely confirmation of a future transaction at a predetermined cost. The contract is secure, efficient, and is set to sustain vulnerability. I'll start with some background and then present the details. This is a joint work with Alex, Roy, and Itai. So, blockchain systems. We have internal tokens, and we have transactions of these internal tokens among the users. And we use the blockchain as the main data structure. This is a linked list of elements called blocks. The system operators include transactions in blocks, and by doing so, confirm these transactions. And while including the transaction in the block, they get the fee that the transaction offers. Fee as in the system tokens. And the system operators, they want to maximize the amount of the number of tokens that they get. Okay, so they optimize which transactions to include. We had plenty of lectures about that. The tokens are associated with smart contracts. These are stateful programs that run on transaction data. And their state changes with these transactions. For example, a transaction can transfer tokens and pay fees. And we say that the user has tokens or own tokens if she's the only entity that can transfer these tokens. The system has this internal metric called gas that measures how complex a transaction is. So a transaction has many operations. Each operation has a gas cost, which is a predetermined amount. And the total gas of a transaction is the sum of all its opcodes. And the thing is, we can only fit so many gas, or so much gas in a block. So that limits the number of transactions that can fit in a block, making block space a scarce resource. And when we have a scarce resource, there is a market, and the market is for fees, how much you pay to get your transaction included. And the way the operators optimize is by considering the fee-to-gas ratio. And there's a threshold for each block, which we call the gas price, that says, OK, if you pay above this threshold, or if your transaction pays, if this ratio is higher than the threshold, then you get included. And if it isn't, you are excluded. So let's look at two graphs I picked from the internet about a week ago. Left-hand side, this over the span of 2 weeks, you can see the gas price being under 20 and then jumping to over 40. Yeah, so it's extremely volatile. And even if you zoom into a span of about 5 minutes here on the right-hand side, this is 5 minutes, you see how much, how you have transactions that offer significantly higher fees than the others. So this is wild, it's volatile, it changes rapidly. You can't really predict what's going to happen in the near future, let alone the far future. And this unpredictability is not just a UX issue, right? This is a security concern, because if your application requires transactions to be included, and you can't determine the price that it needs to be included, then you're at risk, right? You can't estimate what it will cost you. So I won't list all the applications, but rollups, off-chain channels, swaps, etc. All of these require the transaction to be included in a timely manner. And if you can't get your transaction included due to a price surge, for example, your either safety or violation or liveness is violated. So how do we mitigate these price volatilities in regulated markets? The traditional way is to have a future contract. So let's say two parties, a buyer and a seller, are afraid that an asset price will jump either up or down. So they form a contract agreeing, okay, I'll buy from you this asset next week at this predetermined cost. And this works, right? Please take note that one of the parties will be happy because if the price goes up, then if I intend to buy the asset and I agree to pay a lower price than what the later market price is, I win, right? I bought something cheaply. And the other party, the seller, loses, right? He has to sell beneath the market price. And vice versa, right? If the prices go down, I pay extra. I could have bought it in the market for less. But now the seller profits because he sold something above the market price. So if we disregard friction or additional cost, this is a zero-sum game. But we know there are always additional costs. I need a lawyer. The other side needs a lawyer. We need to sign a contract. So it's not, there is always friction. And the thing is that this type of contract is enforced by the regulated market, right? There are courts and lawyers. So if one of the party violates the agreement, I can sue him, right? I'll go to court, I'll sue you, and then I'll get compensated. So can we have this type of contract in a blockchain setting where we don't have courts and lawyers? Well, the answer is yes, because I'm about to present one, but it will be in a few slides. So before having this contract, what can we do? We can resort to hedging the gas price directly. What does it mean? If I'm scared that the prices will go up, I will long the price, and then the profits I gain from my bet will compensate me for the additional costs, and vice versa. So this is a level of indirection, right? I'm interested in having my transaction included, but I can protect myself in this way. Not as convenient, but maybe something to consider. And the way to do that is by using gas tokens. So on Ethereum, we have two types, or we had two types of gas tokens. The first, I think, is slightly more famous. The mechanism works as follows. You store arbitrary data on the storage. That costs you some gas. And then you delete the data, and you get a refund of gas. That works, right? So you can monetize gas like that. And that's great, except it's inefficient, or was inefficient, because the refund ratio was about a third. So it only made sense if you expected the price to go up by more than a factor of 3. And it's also obsolete. As of August 2021, there was a hard fork. They changed the policy. It doesn't make sense to do that anymore. The other type of gas tokens was using a synthetic token. So essentially, you have a token, and you artificially set its value using an oracle. This has many problems. The first, it's really susceptible to DeFi attacks, like all the previous talks mentioned, front running, liquidation, etc. And even without these, the oracle itself is a single point of failure. If you set it to sample the price at a short period, then it's really susceptible to even more attacks. But if you go for a longer sampling period, then it's inaccurate. So that's not as ideal. There was a company that did that. I checked before. Their website is down. Their token went down 99%. OK, so what can we do? Yay, Ledger, our solution, a smart contract. OK, so let's have a smart contract for future transaction inclusion at a predetermined price. We have two participants, the buyer, the one that wants the future transaction to be included, the seller, the party that agrees to pay the future transaction fees. And the main idea is to incentivize both parties to fulfill the contract. We have two phases, the setup phase, which is now let's negotiate and agree on a contract, and then the execution phase. We got to the future, now I want my transaction included, let's get it done. So two phases, setup and execution. And the now and later is determined by the block numbers. Okay, so the system progresses, we monitor the blocks. This is how we measure time. So how does the setup work? We have the buyer. Let me just say, there are plenty of tweaks and variations we can do. I'm presenting one, but you can tweak it around. It works pretty much the same. So in this version, the buyer deploys the contract and sets a few parameters. So the first being the future period. Also, the amount of gas that we're discussing. I make it as gas. And 3 numbers that represent tokens. The payment, which will be the payment that the buyer is offering for the future gas. Epsilon, which its purpose will be clear in a bit. And a required collateral by the seller. When the buyer deploys this contract, he also deposits the payment and the epsilon tokens with this contract. Okay, so it transfers the tokens to the contract. Then the seller can register with the contract, accept it, and by doing so, he has to deposit collateral tokens. Let me just say that if a seller doesn't register, then the buyer can recoup his tokens later stage. Okay, so this is the setup phase. Now time passes, we got to next week. Let's see what we can do. So at this stage, actually, only seller can interact with the contract. There are 2 options, or 2 functions that the seller can invoke. So the first is called the apply function. It takes as input data, or call data, a transaction signed by the buyer. Okay, this is the transaction that me, the buyer, wants to have included in the block. So that goes as a call data to the apply function that only the seller can invoke. What the apply function does is executes my call data, eval on this data, and then transfers all the tokens, the payment, the epsilon, and the collateral tokens to the seller. The other function is exhaust, which just does null operations whose gas is supposed to accumulate to the parameter gas that we set up to begin with. And then it transfers payment plus collateral tokens to the seller. So intuitively, using the first option, the seller gets slightly more tokens. Okay, so payment plus collateral, and here you have the additional epsilon. So seller is supposed to prefer this option. But this option requires that buyer sends a transaction, right? So if the buyer doesn't send a transaction, the seller has a way out of the contract. So this is why we have these 2 functions and the purpose of each of them. So this is the happy path. This is the get out of jail for the seller path. OK, so let's analyze this construction. We consider a game played by the buyer and the seller. There are multiple interactions throughout the setup and the execution. You can send transactions, ignore, not send transactions, etc. We have to take into account the gas price that is randomly drawn just before we get to the execution phase. So we decide on something now, but then next week we have a randomly drawn gas price. And we consider the participants to be utility maximizing participants, where the utility is the expected number of post-interactions tokens. So when we're done discussing and negotiating and posting transactions, how many tokens each of us has. And we also have this exogenous utility for the buyer that motivates him to have his transaction included to begin with. So buyer wants a transaction included. We model this by an exogenous utility function. The solution concept is subgame perfect equilibrium. This captures the ongoing decision-making throughout the execution. More about it in a few slides. OK, sorry. OK, so let's talk about the utility functions. We're talking about hedging and insurance. And in that case, it makes sense to capture the certainty preferences of the participants. The participants prefer to have tokens with higher certainty, even at the expense of having less expected tokens. As an example, maybe I prefer to have 4 tokens with probability 1 over having 10 tokens with probability half, despite the latter having higher expected value. This is the reason why people go to get insurance, right? So we say that both the buyer and the seller are risk averse. And the way to model that is by modeling the utility function to be, well, increasing the number of tokens. This is trivial, but also to be concave. And the curvature measures how risk averse they are. And higher curvature, more risk averse, prefers more certainty. The common examples is the linear, the square root, and the logarithmic functions. OK, so distribution. We need to discuss how the gas price is distributed at the next week. Looking at previous work, only about how to determine the gas price for the next block. Not 2 blocks, not 10 blocks, let alone not next week. So what we do, we use the prevalent random walk price model. This is the standard modeling, as far as I know, which means that in each block, the gas price changes according to a sample from a normal distribution. And that means that the longer I predict towards, the variance grows linearly in the number of predictions I make. Okay, so just keep that in mind. It will come relevant in a bit. And to validate this model, we actually take data from Ethereum, a month of samples. This is about 200K blocks. We use the Kolmogorov-Smirnov test to test if these samples match the normal distribution, and we get really great results. Statistical significance that shows that this model fits. And looking at this data, we see that the mean value is usually 0, and we have low variance. So here's a nice graph that shows that. This is a heat map, okay, that looks like a flame, I know. So we have on the horizontal axis, we have the mean value. On the vertical axis, we have the variance. And you can see that most of the samples are concentrated over here, mean value of 0, and rather low variances. So this this validates the model. OK, so this is the game. I won't go over all the details, but let me just say that the upper part is the setup phase. This is the execution phase. This captures the, sorry about that. This captures the random sampling of the gas price towards the execution phase. And OK, so here we start. The buyer decides if to initiate the contract or not. If not, we get to a situation where there isn't a contract, and then the buyer has to decide if he wants to get his transaction included or not. OK, so this is this left part. If there is a contract, then the seller has to decide if to accept. If not, the buyer can recoup. If there is a contract and the seller accepted, then the buyer has to decide if to publish a transaction or not. If he didn't, then the buyer can only exhaust or ignore the contract, use the exhaust function, or just completely ignore everything. Or if there was a transaction, then there are these two options again, but also the seller can confirm the transaction, what we call apply, and then get the tokens back. So this is the game. And the way we analyze subgame perfect equilibrium games is called backward induction. That means we look at this tree, at the leaves, analyze what would be the strategy, the preferred strategy of each participant in that leaf, and then propagate this upwards until we get the strategy vector for the entire game. This analysis results in the following. One, buyer is always incentivized to publish a transaction because she already paid. And that transaction is always abiding the gas limit that the buyer committed to. Okay, so you committed to 10 gas, you wouldn't publish a transaction that requires 20 gas. That doesn't make sense. Given that, seller always prefers applying over exhausting. So if there is a transaction, seller will always prefer to have that transaction included. He gets the epsilon tokens more, and potentially this transaction requires less gas. And to the question of whether seller prefers applying a transaction or simply ignoring the contract, well, that depends on how much tokens are in the contract and what we got as the gas price at the moment of truth. So when considering, OK, so the intended execution, which is what we want, buyer initiating, seller accepting, and fulfilling the contract, is subgame perfect equilibrium. This will be the outcome of the game, is a function of how risk-averse the participants are. what is the volatility or the variance of the distribution, and the contract overhead, the friction. How much does it cost to interact with the contract? Because if you just go to the market, you don't have these setup and additional costs. And we show that for a wide range of practical parameters, indeed, interacting with the contract is the subgame perfect equilibrium. Let me show you an example. So arbitrary parameters that we used for simulation. We have 3 distributions that we consider. Predicting for a minute ahead, predicting for an hour ahead, and predicting for a day ahead. On the y-axis, we have the required gas price for the contract, or the ratio between the payment that the buyer pays to the gas that we want in the contract. And these bars represent the acceptable price range for both parties. So for the buyer, there is a maximum price, and for the seller, there's a minimum price for which they want to interact in this contract. And the different charts are due to different utility functions. So we have the logarithmic square root and the linear function. And we can see that for the, so first thing we can learn from this graph, the more risk averse you are, for example, if you have a logarithmic utility function, the more you want to interact with the contract. Okay, so we can see, for example, over here that if you have a logarithmic utility function, you accept a higher price range compared to a square root function. And this is also the same for the seller. Also, we see the effect of the variance. If there is a higher variance, because we predict for a longer time, then the acceptable price range is higher, okay, comparing this one to this one. And more importantly, we see that there is an overlap. So there is an acceptable price range for which both of the participants would like to participate in the contract. Now, I'm not discussing the negotiation and what price to agree upon, but there is a range, and this is what we care about. And please note that this is with friction, okay? So we introduced some overheads because of the contract. Let's see what happens without this, meaning what would happen if we could optimize the contract or fully optimize it. And we can see that immediately the ranges grow, okay? So now, without this friction, everything is smoother, and there's more tendency to interact with the contract, which makes perfect sense. We also have an Ethereum implementation. Most of the functions are straightforward. Let me just mention the exhaust function. What it does is a null operation in a loop, simply iterates. We have these 2 seemingly magic numbers. We got these heuristically using a locally ran profiler to overcome the cost of calling this function. Also, we had to compile without optimization flags, but yeah, never mind. OK, looking at the numbers, we see that the interaction is the order of 100K gas. The overhead of interaction is 100K gas, which is orders of magnitude less than what we can potentially hedge for, say, millions of dollars, millions of gas, sorry. And there are plenty more optimizations to be made. You can reuse the contract. You can skip some of the parameters, have them hard-coded, etc. So this will be even better, potentially. And we also have a deployment on Goerli. To conclude, Ledger Edger, a smart contract for future transaction inclusion at a predetermined fee. We have analysis and measurements showing it's applicable and efficient. And we resolve the prevalent issue of unjustified reliance on fee stability. Thank you very much.
Please go ahead.
So in your presentation, you analyzed at length the situation where you have one buyer and one seller. I'm thinking about the situation where you have multiple buyers for a given seller. Could the seller extract value from his buyers because since he has control, like he has the meta transactions and he's able to assemble them in any order, you can therefore profit from that and include some of your own transactions that you as a seller have control over, right? And I also noticed that, so second question, quick question. I also noticed that the buyer is publishing his transaction, which means that third parties are able to observe it and maybe place an order with the seller also for the same purpose of like MEV.
Yeah, so first question first. No, we didn't analyze more contracts being deployed in parallel. We didn't analyze a market of maybe transient contracts. So I'm buying from this person but selling to that person. We didn't analyze the effect of multiple contracts being deployed on the gas price, knowing that there are parties that need to have transactions included at a predetermined, like this essentially tells everybody, hey, there will be a transaction then with this gas cost, right? That affects the price. So back to the question, no, we didn't analyze any of that.
Okay.
Open research question, please join us. Remind me quickly, what was the second question?
Well, so the essence, both questions are really the same question. Essentially, the buyer is publishing a transaction that he intends to have executed, and in fact, that meta transaction is sufficient to be executed. Nothing more is required from the buyer, which means that the seller or anybody else really can take advantage of that information being revealed and in the sequencing of how that is.
Yeah, so that meta transaction is tied to the specific instance of the ledger hedger contract.
Right.
So, yeah, well.
But the seller gets to choose when to execute.
Yes.
Right. Okay. Thanks.
Thanks.
So you said the seller, the miner, has a penalty for not.
Wait. Let me stop you. The seller is not a miner. It doesn't have to be a miner.
Yeah,
okay.
But you said the miner has a penalty of epsilon for not following the agreement.
Yes.
And the gas price follows a random walk. So essentially, there's an option hiding there that allows you to analyze things perhaps in a simpler way than using sub-game perfect equilibria and requiring some knowledge of the risk preferences, right? Because this is exactly an option. You have something that's following a random walk minus the cost of not following it, minus the epsilon, right?
So actually, there's a penalty for the seller to not
for the miner. For the miner, you said?
No,
not for a miner?
No, the seller does not have to be a miner.
No, but the penalty of epsilon is for the miner?
No, it's for the seller.
Oh, okay.
So there are no miners in this game.
So the person who reserves the gas is the buyer?
Yes.
And the person who puts a transaction in the block?
The person that agrees to pay the transaction fees for that transaction in the future is the seller, yes.
Okay, sorry. Never mind.
Cool. Lunchtime?
All right, we're perfectly on time. Thanks again.